All right, let's talk about some other ways of evaluating limits. All right. If it's a polynomial or rational function, then as long as the denominator is not 0, we are pretty good to go. But in the last video, we said sometimes the denominator is 0. What do we do then? And we're going to start by looking at two functions. All right. I'm going to look at two very similar functions. All right. The first one is the one from the last example. And the second one is x plus 1. And you might say, Jason, these don't look that similar, but let's look at their graphs. Okay, the graphs of these two functions. The first one, f of x, is this blue graph. It is a line with a hole in it. The second one is this pink graph. If this doesn't count as pink, then just let me know and say, Jason, you got your colors wrong, but it's kind of pink. That's just the straight line with no hole. So the pink one doesn't have a hole, but the blue one has a hole. This first function has a hole because there's a common factor in the numerator and the denominator. That means a hole, also known as a removable discontinuity. We'll talk more about those in the next video or next section, 2.4. All right. The second one is just a line. It doesn't have a hole. So first one, line with a hole. Second one, line without a hole. Very, very similar. And remember that I always say that when we're looking at limits, it doesn't actually matter what the function's doing here. It doesn't matter if we have a hole for a limit. It doesn't matter if the function's way up here for a limit. So in fact, these two functions have the same limit everywhere. But more specifically, we're going to say these two functions have the same limit near x equals 1. So again, these are different functions. They're very similar, but they are different functions. F and G are not the same, but they are very close. All right, almost as close as you can get without being the same. All right, so they are the same as x approaches 1. Okay? And again, as x approaches 1, it means x, we're not actually talking about 1 itself. We're just saying they are the same as x gets really close to 1. Right? Pink and blue are the same as x gets really, really close to 1, but we're never including that limit point. Whenever we talk about limits, we never get there. We only get really, really close, all right? It's like, you know, I don't know if anyone was a kid in the back seat of a car growing up and I'm not touching you, but ugh. That's what these functions are doing. That's what these limits are doing, okay? So we're gonna say, and there's a little bit more in depth of a property that the book talks about, but in general, this is what we're gonna be able to say. That their limits are the same. And again, the book goes into the more in-depth reason for this. We're just going to use that fact, and you can check that out if you want some more information. Again, it's going to be down here a little bit. It actually uses the same example and tells you more about why we can do this here. So let's do some examples and utilize this. Example 3, evaluate following limits. Part A, the limit as x approaches 3, lots of 3's today, of x squared minus 3x divided by 2x squared minus 5x minus 3. Whenever you're evaluating a limit, especially if you see that it's rational, check in your mind, can I use direct substitution? If you can use direct substitution, this is a rational function, and you can use direct substitution if it's rational and the denominator is not 0 at this place. If you can use direct substitution, use it. All right, so try always. Because that's always the quickest way of solving these problems. So let's just look, you know, real quick. Okay. When we plug in, if we plug in 3, what does the denominator do? 2 times 3 squared minus 5 times 3. minus 3, that's 18, minus 15, minus 3. All right. What a surprise that in this video, Jason would give an example that does not allow us to use direct substitution. But it's a good habit to be in because it can make things quicker, make things shorter. So we can't use direct substitution. We're going to have to use a more advanced method. Specifically, we're going to use this idea. We're going to say, can we write this as a very, very similar function? What's the difference between f and g? Well, g is just what happens when you factor f and cancel. Let's look at that here. Let's factor. This is the limit as x approaches 3. On the numerator, we can take out a common factor. You might have to review your factoring for this class. Algebra is very huge in calculus. Factor out an x. What are we left with? Factor out an x, we're left with an x. Factor out an x, we're left with a minus 3. The bottom, well, that's a little bit trickier to factor. Okay, it's going to be a 2x, and it's going to be an x. The AC method is a great method to do this, to use here. You can also use the guess and check method. If I guess and check, I put a minus 3 here as my guess. The reason why is because I have a 2x and a minus 3 now. That gives me a minus 6x. And then I'm going to guess a plus 1 because that'll give us minus 6x, which we wanted, and a plus 1x. That gives us that minus 5x. And if we look at these last two products, it also gives us the minus 3. AC method or guess and check method is a good way to doing this. You can ask me for more resources on that if you'd like. So now, another way to do a guess and check method is to say, I'm going to guess that there's a common factor. So, don't write this down just yet, but just watch. If I do this, I'm changing the function. They're common factors, but this current function is not defined at x equals 3. If I cross these out, the new function is defined at x equals 3. It's changing the function. Just like blue and purple are not the same function because one has a different domain. One is defined at x equals 1 here. But their limits are the same. In fact, this is the same as when we cancel literally everywhere except at 3. So it's equal to this as long as x is not 3. So we can say this is true because x is not equal to 3. We're only looking as x gets really, really close to 3. So this is a very good thing to include in your work. I'm not going to be taking points off if you do not include this, but it's a very good habit. And now we have a rational function. Let's try the direct substitution method. So as long as the denominator is not equal to 0, so let's try it. If we plug it in, we get 3 divided by 7. Okay, great. Again, you can use, however you want to call it, properties of rational functions. You could call it something else, as long as you explain. And again, the denominator is not equal to 0. However you want to word this explanation. So this limit is 3/7. And you could check this with Desmos as well. All right. Let's introduce one more method. One more new method. The limit as x approaches -1 of the square root of x plus 2 minus 1 divided by x plus 1. Again, tons of algebra in this section. Tons of algebra in this class. And this is going to be some more. So this is not a rational function. The bottom's a polynomial, but the top is not a polynomial. This is not a rational function. We can't use polynomial law or the rational theorem, whatever the book called it. We can't use that. We could use limit laws, but either way, we're going to run into a problem. Because if we try to use limit laws, again, we're going to be dividing by 0. If x is -1, the bottom is approaching 0. The top, it turns out, is also approaching 0. So again, if we try direct substitution here, we're going to get a 0 over 0 situation, which is going to cause some problems. So we're going to give another trick. And again, I do not expect you to look at this problem right now and know what to do. But at the end of this video and at the end of the next video, we're going to talk about patterns to look for, and you'll eventually be able to look for those patterns and find out what to do here. Okay, so in this case, we're going to do something that we've done before in math. We're going to multiply by the conjugate in order to get rid of the square root. We've done this before when rationalizing denominators, multiplying by conjugates, and also simplifying complex numbers. You may have seen this before. We're going to multiply by the conjugate of that numerator because we want to get rid of the square root. Multiplying by conjugates always gets rid of square roots. And when I say conjugate, I mean, look at this and look at this. They're almost the same, but one is subtraction and one is addition. That's how we multiply by conjugate. All right, but if we want things to be the same, and indeed we want the next line to begin with an equal sign, we're doing it on the top, we have to indeed do it on the bottom as well. So we're not changing anything. Equal sign is preserved because what we're doing to the top is what we're doing at the bottom. Now, be very careful when simplifying this. You're going to have to FOIL it out, but there are some shortcuts. This is what's known as the difference of squares. And for purposes of time, I'm not going to spend too much time on it now, but you can ask me if you're curious about this step. This is going to become the first thing squared, which is just x plus 2, minus the second thing squared, which is 1. That's the difference of squares shortcut I'm using right here. You can also FOIL it all out, and things will cancel. And on the bottom, we do have to distribute. All right, it's going to be x plus 1 times this, and x plus 1 times that, and the bottom is going to be a little messier. X plus 1 times the square root, plus x plus 1 times 1. Now, it doesn't look like we've made anything better for ourselves. In fact, it really doesn't look like we've made things better for ourselves. I haven't done this problem recently. I'm pretty sure we've made things better for ourselves though. So let's simplify a little bit more and see where this goes. All right, so this is the limit. As x approaches -1, what happens to the top? The top becomes x plus 1. The top becomes x plus 1. Yes. It's fine. And the bottom. So, all right, let's look at where we're going here. The bottom's a mess. We can't really simplify the bottom because it's hard to interact between a binomial and a square root. So in fact, let's unsimplify the bottom. Let's keep the bottom factored. All right, let's factor the bottom again, make it look like it used to. X plus 1 times the square root of x plus 2 plus 1. So if we factor the bottom, it would have been easier if we just never distributed it at all. If we factor the bottom, we have something really nice. Cancellation. They have common factors. So again, canceling changes the domain of the problem. And in fact, multiplying by algebraic expressions also changes the function as well. But as long as x is not equal to -1, these things are going to be the same. So we're going to cancel. This is the limit as x approaches -1. When we cancel, the top just becomes, right, it always cancels to 1. The top is 1 and the bottom is the square root of x plus 2 plus 1. And again, the reason why these two things are the same Since x is not actually ever equal to -1, we're only looking at limits. X is close to -1, but not actually equal to it. And as long as x is close to -1, these two things are the same. And again, even now, it doesn't look much better than what we started with. But since we canceled, maybe we can use direct substitution now. All right, or limit laws technically. Can't use direct substitution really because this is not a polynomial or a rational. So really, we are going to have to use limit laws to finish this one off. So this is going to equal, because if we plug in like this bottom, if we plug in, we're not going to get 0. So we can use limit laws, no problem. It's going to be 1 divided by the limit as x approaches -1. I'm having some issues here at the bottom of my tablet of square root of x plus 2 plus 1. And again, this is the quotient rule. And again, the reason we can use the quotient rule is the denominator is not equal to 1. Not equal to 0, I mean. The denominator is not equal to 0, so we can use the quotient rule. And then we'll use the sum rule, and then we'll use this power rule, and then we'll use the sum rule again, and so on. And again, we did enough of that in the first video, so I'm just going to write a dot, dot, dot. After you use more limit laws, you're eventually going to get 1 over 2. All right, more limit laws. I don't want to spend the time in this video because we already did that enough in a previous video, and this video is already getting kind of long. Okay, so again, we can't just skip to direct substitution really because it's not a rational or a polynomial function. On the quiz, I'm only going to give you a short limit laws problem. I would not. I'm not going to have something like this pop up probably. Or if I do, I'll say you can use direct substitution even though we haven't proven it yet. All right. But that's the idea. I also do want to technically be correct. So I'm going to say, yes, technically we're supposed to use limit laws here. But I'm going to be restricting my use of limit laws for only a couple problems most likely. So let's summarize this video with some techniques. We talked about 2 techniques in this video. The first technique we used was to factor and cancel. We actually did that in both of these examples in this video. So this is something to be looking for. If you cannot use direct substitution, if you cannot use that theorem for polynomials and rationals, if you cannot use limit laws, try factoring and canceling. If that doesn't work, try multiplying by the conjugate. That's what we did in the second video, or second example in this video. And if that doesn't work, do 3 or 4. What are 3 or 4? Good question. You're going to have to wait until the next video. Gotcha again. Cliffhangers all over the place in this section. Have a good one and let me know if you have questions.